Hi everyone, welcome to a new set of videos on graph implementations and traversal. In the previous set of videos, we discussed the graph terminology as well as the different properties that is associated with graphs and the types of graphs. Today we are going to continue with this topic of nonlinear ordered data structures, which is graphs. We are going to discuss the graph implementation, the performance of these different types of implementations, and how we traverse the graph data structure to solve more interesting problems. So, just a friendly recap, we discussed the fact in the previous lecture, which is graphs is an ordered pair of set of nodes called vertices and a set of edges. So let's start with the graph implementations because we discussed more theory last time. So we are going to discuss more about the implementation. And the way we are going to start is first we'll generally describe how the different implementations look like. And then we are going to see some C++ code on how to actually implement them in C++. So before we get started, I just wanted to let you know there's no common like graph API, which is API is an application programming interface. It is you can think of it as the features that are available out of a program for the user, which is what kind of functions can user call without knowing the details behind the scenes, which is we don't want the user doesn't care about like whether we are manipulating pointers, whether we are deleting memory behind the scenes. What the users care about is how do I add a vertex, how do I remove a vertex, and so on. So there are no common ADTs for graph, which is the abstract data type. And the reason why the ADTs is not there is because graphs were were present much before object-oriented programming paradigm, which was object-oriented programming was probably invented in like late 1970s, and ADTs came after that. So graphs were used much before that. So whenever we are designing our own graph API, it must include the different graph methods as well as the signatures of those methods, which is what is its return type and what kind of arguments can be passed into this method. When we define this graph API, we are always thinking about how the client is thinking, which is what is the user expecting to do with this graph. And we are consciously making choices about an underlying data structure which can be used to represent the graphs, which is in our case, there could be multiple data structures we can use. We can use vectors, maps, arrays, and we need to think about it carefully when using a particular data structure because our choices can have profound implications on the runtime, which is the time complexity, as well as the space complexity. Another thing that we care about is the difficulty of implementing various algorithms. So we don't want our code to look so arcanious that it kind of like obscures how we are solving the problem, and it's like difficult to debug as well as maintain. So before we go move to the actual implementation, one quick thing I wanted to let you know is it's a common convention to represent graphs by numbers, which is like in this graph, like this is the graph from the project 2, which is the PageRank project. So basically, we have URLs that are something like google.com, facebook.com, and so on. But representing this in the form of numbers is more commonly used. And the reason why it's that is because whenever we are actually representing all these graphs in memory, they might be represented in some array or some other data structure, and it makes more sense, or it's much more easy to represent these by numbers or indices rather than by the actual like string names. So how we can solve this problem is we use something called a map data structure. This data structure we'll cover in depth in the week right after this, which is like once we finish graphs, we are going to start with the map data structure. But for the sake of discussion, it's pretty trivial. So I just wanted to let you know we won't be discussing the implementation of maps, neither how the performance can be derived, but we are just going to use this map data structure. And how maps work is maps are basically associative arrays or like dictionaries in Python. Some of you might already be familiar with it, which is They act like a table, and it has two different columns, which is one is the key and the other one is the value. So in this case, like let's say if we have some strings that a problem that we are trying to solve has some strings, which is like in this case Gmail, Facebook, Google, and so on. We can represent these keys with this these strings, which is Gmail, Facebook, and so on, can be our strings. And we can represent the value with a number that we define as we go. And we are going to see like how we are assigning the numbers. As we are reading the data, we can assign numbers, which is this Gmail maps to 0, Facebook maps to 1, or so on. Like I'm just giving you an example. Here I have the actual like graph indices I've mapped to. So these two graphs are exactly equivalent. It's just like a one-to-one mapping. Now, the way to get these indices is pretty straightforward in maps. So let's say if you define a map in C++, uh, let's call this like M. You can define this just like this is the data type, which is map of strings and keys, because we have strings as the keys and integers as the values. Now, if you want to insert an element into this map, like let's say if you want to insert like google.com, you can just do something like M of Google, in our case, is equal to the value, which is 0. Similarly, if we want to get a value, we can just do something like M of Google. And if we do print this value, we are going to see like we get the value 1, and so on. So all the vertices that we have, the gist of all this information is that like all the vertices, whatever form they might be, like they might be an object, they might be strings, they might be long or some other type of uh, values, you can represent them by an integer label, which is you can have a map that maps from the label, like it maps each label to a integer value. So let's start discussing the different common operations that are associated with graphs. And let's move on to the implementations by discussing these common operations. So whenever we are designing any particular data structure, we consider like what are the most common operations that are used on that data structure, because that defines like how are we going to implement it. In this case, these are the most popular kind of operations that are there, that are present when we are discussing graphs, because you see these operations again and again when you are implementing different algorithms. So the three types of implementations in C++, or generically, we are going to discuss those implementations by talking about like how these common operations behave in those implementations, which is the first one is connectedness. And what I mean by connectedness is, let's say if we have two nodes, A and B, and we ask this question whether A is connected to B or not. Or if we have another two nodes, which is A and F, are they connected or not? The second one is neighborhood or adjacency. When we are discussing neighborhood or adjacency, what I mean by that is what are the neighbors of node A? So how fast can we tell like what are the neighbors of node A? The first one was connectedness, which is how fast we can tell whether A is connected to B or not, like directly. I'm not talking about whether there's a path from A to F or A to B, but I'm talking about whether A to B are connected. So let's say if I ask like whether A and B are connected, this should return true because they are. If I ask something like A to F are connected, that should return false. Similarly, like this is a directed graph. So if I ask this question whether B and A are connected, this should return false because the direction is from A to B and not from B to A. But generally, we are going to discuss more of the undirected graphs in the most problems that we are going to see in the different forms of implementation. So in the next video, we are going to start discussing the three common representations, and we are going to discuss the behavior in terms of connectedness as well as adjacency, which is, let's say for adjacency, if I ask what are the neighbors of A, it should return B and C and so on. And the three common representations that we are going to talk about is edge list, adjacency matrix, and adjacency list.